Now, then I have kBT ln q to the power n is n ln q, then because there is q to the power n and minus ln factorial. This n comes because there is exponent here in qn, and this comes because n factorial. Then what is something is jumped here, but I hope you will be able to do that. I put now q to the power, this is q, my q, so q to the power n has become small ln q. So these become what we have in the last page. This quantity you have to do n ln n by n e to the power n, all these factors come here, and this n becomes n kBT, this factor that is here with h square everything. This thing that ln v by e, that ln v is not from there, that v comes from this v. All Starling's approximation gives this factor v by n to the power e. That is plays a very important role, as we will see right now. So if this is the free energy which is following from this, from there we do this is a little unstable, from this then we get this, then we take the derivative, the pressure minus dA dVT, and thermodynamics, then we get, if you do that, then all these things, since they are log, all of things, these don't matter, these don't matter, I just get 1 over V, because it is ln V, 1 over V then gives n kBT by V, and this PV n kBT. So this is the ideal gas, which was written down by people from Boyle's time, from 1830s or 1840s, something which Maxwell used, but there was no derivation. PV equal to RT was a derived, kinetic theory of gas derived it by using, remember P equal to 1/3 mc square, and then you put a c square there, you get this quantity. And but that is, I told you, kinetic theory of gas had this kind of strange set of assumptions within it. It does not interact, but at the same time it has a size, and it is interacting with the wall, having a elastic scattering like a billiard ball. As the basic idea that it is a non-interacting collection of particles, and that gives rise to this ideal gas law was proven. So these are the, as I told you in the beginning, these are beginning of the applications of statistical mechanics. So this is one of the result. Then this next result is that this is very important thing that I told you, Circulatory equation, and the Circulatory equation follows trivially. Then you go now take it with respect to entropy is negative temperature derivative of free energy, okay, and that when you do, I take d dt, what I can see what can happen, I can it can, this is t to the power 3 by 2 here, so that will become t to the power 5 by 2. So first term I take dA dt, first term will just remove this term and have n kb ln 2 by kt 3 by 2, okay. Then second term n kbt remains n kbt, I go and do derivative of this term. When I do ln there inside, then all these things disappear, they are log term, I do not have to take care of them, I have to take care of 3 by 2. 3 by 2, when I take a derivative, it becomes 3 by 2 comes out and it becomes t to the power 1 by 2, because ln t 3 by 2 1 over t 3 by 2, and then you can combine the, and the 1 t there that comes in and that hits you with the 3 by 2. So that again become 5, okay, 1 by 2, the 1 by, this become 1 by 2, you hit by again t, it again become 3 by 2, and when you do that, ultimate result is 2 pi by, I am not deriving, it is fairly trivial, but you can do it because it is just ordinary derivation. So this quantity, this is the expression of entropy of an ideal gas, which plays a very important role, we will show right now, is called the Circulatory equation. this equation is given when the volume constant, but I can use this equation, it is within ideal gas. I can derive more useful equation, which is this equation, which is not given in your textbooks. You use volume, PV equal to NKBT. So, if PVT is NKBT, V by N is equal to KBT by P and then KBT by P. Okay. So, this is the one that is used because most of the time we are working with NPT ensemble or NPT. So, in that case this is the Circulatory equation. So, please ask me if there is any problem, if there is any confusion in deriving this equation. Everything clear? I am not doing it A by I, line by line, but I have explained to you how taking derivative of that you get this term coming out. Log is preserved here because first is this term, and then you have the A term, everything remains log, and KBT ln terms remain, then that become 3 by 2, that is why 3 by 2 comes, then it multiplied by that is absorbed, the extra term that comes has been absorbed here. Remember ln 5 by ln E 5 by 2, what is that? What is ln E 5 by 2? Exactly 5 by 2. So that term, these were absorbed, the 3 by 2 factor is absorbed. Okay. So that is, this is a very elegant and nice result, which as I told you in the beginning, that is widely used these days. Many cases is widely used, and amazing that such simple result can find so much use. And what is more useful than this, which is not usually given in textbook, is this quantity. Except one book who uses that. That is why when researchers write books or give courses, this is a little better. The one place I found, it is not in Macquarie, not in Hill, but I found it is in Ben Widham's new little book for undergraduate statistical mechanics, very popular book, just about 100, not even 100 pages probably, but he did actually only up to the atomic gas and a little bit of that, not beyond that, elementary level, but he has this equation. I needed this equation because when we were doing theory of nucleation in a constant under this condition, which is the experimental condition, right, much of our time, then I needed that. That is where I came back, and I was very happy to be able to, I did it myself. I was very happy, the trivial step, but sometimes doing something new trivial is very nice. Okay. So, Circulatory equation, there are many applications as I tell. One is evaluation of the entropy of ideal gas, which is used in these, let me write down this. This is in toto from my StatMac book, line by line. Probably the mistakes you find here mistakes will also be there. So, please just go through the book once and let me know if there are any mistakes. So, the diffusion is called Rosenfeld Scaling, D, or I sometimes put the effective diffusion in an interacting system is A e to the power B A S x, and then S x is entropy minus ideal entropy. There is one more application which I have not written down because it was not written in the book. So, this is actually cut and paste from my book. So, this beautiful relation is called Rosenfeld scaling. This is big. Lot of papers are being written on that on the last 5 years or 6 years. And if in a liquid or dense gases, these equations works surprisingly well, but so one plots this quantity against x. So, you can understand one thing, S ideal is the maximum entropy that it can have. So, because of correlations and order, entropy decreases. So, Sx is negative, more it becomes negative, more the diffusion decreases, and it describes the results exceedingly well. And where I was saying that, where we had to use it in a gas liquid nucleation, there we needed this free energy calculation, G means Ts, and when a low temperature gas is going into liquid, then the free energy of the gas has both entropy and enthalpy. You can make an approximate assumption that entropy of the gas is given this quantity, and that's where in nucleation it is widely used. You can, there is a book, I forgot the name, or several books on nucleation, you will see that use. Now, and beautiful result, I think it is done very badly, that from here specific heat is the temperature derivative of entropy, right? ds dt is specific heat, T ds dt. And I can do that now. I can go, I do ds dt, do the derivative here, and then ln term, there is no temperature here now to complicate things. So just ln T to the power 3 by 2 plus other things are here, they disappear when I take the derivative. I just have ln T to the power 3 by 2. So that becomes just like before 3 by 2, and ln T becomes 1 by T, and then it comes in denominator, and then very interesting, it comes in and leaves me 3 by 2 term, just like before. Then this T removes that T in the denominator, is that clear? And then I have 3 by 2 comes from this 3 by 2, I have a nkb, so specific heat is just 3 by 2 nkb, when n is Avogadro number, Cv is 3 by 2 R. So this is the derivation of the ideal gas law. So the two, these are really beautiful stuff which everybody should know by heart, because you will use them always when you start thinking about interacting systems, start thinking with the ideal gas. So PV equal to RT, Cv is 3 by 2 R. So these are the two things that we, so the things that your first year undergraduate physical chemistry, that comes out from a rather sophisticated thing, but you of course understand when we introduce such a sophisticated thing, this was not the goal of statistical mechanics. This is kind of things on the way. These are kind of rewards you get, but that's not how you started. You didn't start to explain ideal gas. You start to explain interacting systems. We start by Newton's equation where there are forces between atoms and molecules. But these are the way we got, and it just makes you life happy that okay, we understand what you are doing and we are on the right track. Okay. Now some things which are really very nice we should know. So example, translation entropy per particle, these are huge, that's what I am saying. So neon, this is 17.59, these are all given in my book. See, most of the StatMech books are done not with too much affection or love for this ideal gas. There's a strange language to use, but you should feel good about it. Okay, and so asymptotically I can get the entropy from a low density neon, that's doable, and these are very nice agreement of the why you chose neon, argon, krypton. Can you tell me? One very good answer. Second, exactly. So they are the good example of ideal gas. So exactly, that's a good answer. Yeah. So it agrees with the experimental values. Okay. Now, if a canonical system graded into, then we can go to grand canonical, which we did the other day. This is the grand canonical. Sum over it is just mu n kbt, right? This is z to the power n actually, fugacity. So this is the grand canonical partition function. And then one can get the total number of particles and another expression for a chemical potential. This is extremely useful in the density functional theory, exceedingly useful. So I can go from your grand canonical partition function. Now I take the grand canonical partition with respect to chemical potential, the conjugate number, I get the average number of particles in the system. Okay. And then I can write a log of and make that into a density. V, I can bring V here. So n by v is density, and I have e to the power beta u, then I take the log. Then this is extremely useful quantity where chemical potential is given in terms of logarithm. And you guys know that this is the expression undergraduate physical chemists to use, that chemical potential logarithm of density. You remember that? Of course, we didn't understand, though Castellan is the best book on physical chemistry. Even Castellan, that's where you can understand. But even then, there was no meat to it. Why did we write chemical potential, the first term, in a non-interacting system, ln rho? This is the beautiful equation that comes out. So, chemical potential is given in terms of density as a logarithmic term. Oh, lambda is this, lambda is de Broglie wavelength, 2 pi kbt, m kbt by h square. Sorry, thank you very much. So, lambda is 2 pi m kbt by h square. So, let us say m L square by T square, then everything else, these also have m L square by T square. So, I think this half, that's the length scale, exactly, that's what I was trying to do here. So, it's a de Broglie wavelength. That comes out naturally. When you do these things, the length is always sitting there. I could have introduced and I should have introduced there, but doesn't matter. So, this is a beautiful result, a gem of a result that chemical potential. So, is the change in internal energy on addition of an extra particle when entire volume are kept fixed, you know. So, all these things we don't need to do at this point. So, we have got this important result, and then another important result, we write it down here. When I studied, the reason I am so excited I am talking about it, when I studied statistical mechanics, nobody told us that this will be so important, and we had to go back every time chemical potential has to have the dimension of, and this has to be dimensionless, and this has to be dimension of energy. Okay, always keep a on dimension, because you know, if you cannot do analytical work, I am telling you, when you go to postdoc, you will be in miserable shape. Everybody expects, because they do it from, I have seen in my not so bright American colleagues, my students, they are very good in very basics, because that has been, they repeat these things from a 7th or 8th grade and all the way. Even after going to PhD level, I had to take thermodynamics twice, and there they take thermodynamics 10 times. So, they just grind it into you. You better know how to do very simple things. Okay, yes? That's what we will do next. Microcanonical is that, because for getting the microcanonical, you need the energy levels. But a microcanonical anyway I can do without a omega, you can calculate by integration over the phase space. When you do that, exactly same result comes out. For example, I want to get the, that's the one I want to do next in a very elegant way. The elegant way also allows me to establish connection with, so what is omega? Omega is the volume of the phase space. So that means, given a volume V and energy E, I have to now, it's a little difficult because say dr1, and I will do that in a, this is a very good question. That actually brings out why microcanonical is difficult. So I have the kinetic energy putting in here now, but when I have NVE, I don't have this term at all. Instead, I have H has to be equal to E, that constraint, and that's a difficult constraint. That means I am within a volume in phase space. So I have to impose that constraint. That becomes very difficult. We just did it in one of the calculations. Well, we did it also before many times, but there is another way of doing it, which is that in quantum mechanics gives you the energy levels, where you can put this constant much more easily, that is particle in a box, and then you can get the microcanonical partition function quantum mechanically, and that gives you essentially the same result. Okay.